Hi there, my name is Spade, and this is an intro to Opus Magnum bot coding. About 2 months ago, Panic launched the 24-hour Opus Magnum Challenge, a competition to make a bot to play the game with no input. It immediately piqued my interest. I like coding, I like Opus Magnum, it sounded fun. When I looked at the files linked in his post, though, I pretty much immediately gave up. It was like half an hour at most. There was some documentation there, but I didn't have a starting place, so I moved on. I checked back in a few more times, but it was the same story. I just didn't have any luck starting. It wasn't until I chatted with Biggie Mac 42, who's an Opus Magnum icon, that I actually got anywhere. She walked me through some of the key pieces of initialization that actually get a bot off the ground. Purely due to her help, I actually have a bot that can solve some puzzles now, and which hopefully will be able to solve every puzzle pretty soon. But it's wild to think how close I came to just not making a bot at all. It felt one of the coolest non-professional coding things I've ever done, and I hate the idea there's another engineer out there that's just one push away from making something really cool. That's why I'm making this video. This video will explain the basics of interacting with Opus Magnum through Python. I'll then show the logic behind creating a simple machine in Python that changes based on a given reagent. Lastly, I'm going to talk about some high-level concepts that could theoretically be used in a bot implementation. This video won't showcase a full working bot, but I do hope it inspires someone to give it a shot. Without any further ado, let's go to the post to kick this whole challenge off. This is the Opus Magnum 24-hour challenge. As you can see, the post has a lot of rules and specifics about the competition. Most of it doesn't matter to us, but this paragraph right here is important. I'm going to go ahead and download the 24-hour sample pack and om.python, which are the two most important links on the site. Opening the sample pack, we can see 100 generated puzzles. Now the fact that these are generated is important as it allows us to more easily interact with them in a solution file format. So I will show you how to install these very soon. Similarly, opening the opusmagnum.python file shows us this, which is basically code to help simulate the game, or more accurately, take files and put them into more human-readable versions. You can see at the top there's a lot of documentation, then in the middle it's going to be the more human-readable stuff, and at the end we have some more bit code and stuff that has to deal with basically taking files in and out of binary. All in all, this stuff is very interesting, and I think it's very cool, but you don't need to understand how the majority of opusmagnum.python works to use it in your projects. Our first step for puzzle solving is going to be putting the generated puzzles into Opus Magnum. As you can see on screen, this is the file location for where you should put your puzzle so we can interact with it. When you do that, copy down the path you took because we're going to be using that path to access it later in our code. As you can see, for me, I've copied Gen 0 and Gen 1 in, and I'm going to take this path and copy it for future use. Now it's coding time. Let's create a new Python project. I'm going to call mine bot tutorial. And we're going to create a new window. There we go. Now the first thing I'm going to do, hop into this path and add opusmagnum.python. And there we are. We can pop this open and check. And to test that this is working, let's type import om. If that runs successfully, then there we go. We now have Opus Magnum running in our main file. All right, let's get coding. This first part is the part that Biggie helped me with. Obviously without this, we have no puzzle object, no solution object, and no real way to move forward. So this is a pretty important first hurdle. Let's start by creating a puzzle object called puzzle using the om.puzzle method. This takes a path as an input. Let's put that in quotations. And we now know that we're working with /gen000.puzzle. All right. As you can see, these backslashes are causing us some problems. Let's put an R right here. That just makes this a raw quotation and means those backslashes won't cause us any problems. Next, let's open up solution and make a solution object in the same way, except that we obviously aren't pulling a path. It's going to be the method. Now, let's do solution.puzzle. We're going to make that, obviously, the puzzle name. This piece right here, it makes sense if this is confusing. This is kind of the step one. Once you have this, you never need to do it again. It's a little bit strange. I will give it to you, but just trust the process, and once we do it, it will work. We have a puzzle name. Next, we're going to do solution.name. And this can be whatever you want. It's going to be a bit string, though. I'm going to do spadebot because I feel like it. Next, we're going to do solution.parts. Now this, if you're curious, is actually the entire bot is going to be producing this list. Right now it's going to be an empty list, but pretty soon we'll hopefully have this list be extremely full with all the components we want our bot to have. Lastly, let's do solution.write-to-path, and we're going to do that same path as before, but we're going to leave it at the numbers, slash, and whatever we want to call it. I'm just going to call it gen000.solution. With that code written, let's actually open the game and see what we have. As you can see, here is our puzzle. Your puzzle might look a little different than mine, but overall it should work about the same way. We're going to open it. We're going to see new solution 1. Nothing is in here. If we run our code, however, and press F10, which reloads all files, if we leave, there it is, there's SpadeBot. This file was created by our code. Anything that we now write in the code will appear in this file in real time. I'm going to pop back to our code, and instead of using this empty array, let's instead call bot, which we can then define up here. And we're going to have it return the same array. Now, of course, we're going to have puzzle as an input, just because we want to be able to use the input. There we are. Now let's instead create something called solution, or let's say part array, and have it return part array. Now, in theory, we can append things to the part array, and it will appear in the final solution. So let's see how we can write the code that will let us put a piece into the file. We don't need to scroll long in the documentation before we find this right here, om.part, with the name being equilibrium and the position being 5, -2. Let's see what happens if we put this into our code, appending that onto our solution. Popping over to the game, if we press F10, we'll see that a piece appears on the screen, and that is how you know that your bot is currently working. Now, how does the coordinate system work in this Opus Magnum? Well, let's check. Let's run 0, 0. Let's run 0, 1. And let's run 0, 2. Now, obviously, height is weird in Opus Magnum. What do you think is going to happen here? Let's run it. And if we press F10, we can see that this is the Y direction. We can do the same thing, of course, but running 1, 0 and 2, 0. And we can see that this, unsurprisingly, is the X direction, meaning that these are the two axes that coordinates use in Opus Magnum. If you want to build in this direction, you'll need to change both the X and Y directions at the same time in order to basically have a straight line. With this understood, you actually have the basics of Opus Magnum programming. In theory, if you wanted to, you can take a break now and go try to build your own system, see how far you can get. If you want to stick around for the ride, let's build something a little bit more complex. Back here on the coding front, we can see that om.part has a few attributes. We have name, which is of course going to be equilibrium here, and the position, which is basically where we're going to put the piece. That being said, obviously some other pieces are going to have more attributes. Things like arms, for example, have a rotation, a length, instructions, and a hex, for example, has to tell you what hexes to hit. Let's go ahead and look at the full list of attributes right here. Obviously, we have the first two we talked about, the part, the name, and the place. But length and rotation are about what you'd expect. The ones that you might not have thought about are which reagent or product. If you're going to put a reagent down, you want to have 1 through 4. Otherwise, or 0 through 3, I guess, I apologize, 0 indexing. We also have the instructions for an arm. This is the hardest part. I will gladly explain this later. And then we, of course, have track hexes. These three have their uses, I'm sure. I have not touched them yet, so we will not be covering them in this video. However, I'd imagine it's worth learning about them. On top of that, here is every piece you can have. These, of course, are the 1 through 6 armed arms. Probably a better way to explain that, but of course, you know, the multi-arms. Piston, rack, the burlo, the bonder, unbonder. I'm not going to read all of these, but these are all the parts you can put using om.part. All right, with that, let's look into hexes, because hexes are more difficult than you would expect. Copying over that track hexes part, we can see that this is a list of tuples, basically of all the coordinate points you want your track to hit. So if we were to append a track, it would be part.track. Position would not be used, but instead we would use track hexes. So let's sub that out right here. Boop. Track hexes equals this. If we run our code, let's pop over and see what happens. We press F10. There it is. There is a track from 0, 0 to 0, 1 right here. Obviously, it's on top of the equilibrium. You can do that weird illegal stacking with this code, but that is an option. You know, if you have 0, 0, and 0, 1, it will create a track. Now, what happens if we were to use some illegal coordinates? What happens, if, for example, if we go from 0, 0 to 3, 5? Miraculously, it does it. If you place an atom like this, there it goes. It teleports. And in fact, it actually has collision as it does so. Hulk. This is one of the coolest things. Now, of course, if you ever have a legal track in your path, your bot will immediately be disqualified. You can't be using this in the competition. That is not allowed. But it is pretty cool, isn't it? Look at that. All right. So that means that now we know that the track hexes, tuples, need to be continuous. And if they're not continuous, you could literally have your solve be disqualified. So make sure that when you're using track hexes, these numbers are very carefully calibrated. The next thing we're going to look at is the instructions. I'm going to copy this over and put it right here. Now, let's format that in the way we've been doing it already. By taking that and now, as you can see, it doesn't like that already, but that's probably because it's track. So let's instead make that arm1. Instead of track hexes, of course, we're going to be using position again, which is just going to be 0, 0, and 0, 1. And there we go. We have the name, we have a position, and we have instructions. Let's make that 0, 2, just so there's no conflict. Now, as you can see, we have G, R, capital G, and capital R. Obviously, not knowing what this is, we'll be able to guess that G and G are probably the grabs, and R probably the rotates. However, if you want to be sure, we can scroll on down to right here. Oh, that's the wrong one. Keep going. Here we are. And you can see the translation codex. I will be making a more readable dictionary later in the code. But for now, we're going to run it as is and see what happens. Hopping back here, pressing F10, we can see that we have a bot that drops, turns, grabs, and goes back. Now, this is not the optimal way, in my opinion, to do this. We're going to create methods that make writing this instructions a little bit easier, just because, you know, it is annoying to have to type this out every single time. Now for the last part, before we get into some more serious coding, I'm going to explain what this puzzle can actually do for us. Let's check puzzle dot and see what we get. And we can see reagents and products are the two big ones. So I'm going to write reagents, and let's run through that as a for loop, or reagent in puzzle.reagents. What happens if we print the reagent? Let's see. Like run, we can see that it is just an object. However, does reagent have anything interesting in it? It does. Okay, well, it's not showing up, but reagent.atoms is another list. Let's do for atom in reagent.atoms. Let's print the atom. I promise we're getting somewhere, even though it looks exactly the same, but now it's an atom object. All right? Well, what does atom have as a type? Let's run that type really quick. And we'll see the type is 1. Now what does that mean? As you can see over here, 1 means salt. And as we know from our Opus Magnum, we have our salt as our 1 reagent. But let's see what happens if we instead add a fire and earth onto it. And there we are, 1, 4, and 3. Of course, 4 being fire and 3 being earth. So this is how we can get information out of our reagent. This is a very interesting and important piece. However, you might notice that they're not in order. In fact, I believe this method uses a linked list, meaning that it will traverse down whatever path it uses as a depth first search, meaning that you can't reliably get the order of the atoms out of it. So how can you figure out where an atom is? Well, luckily, atom dot position exists. So now we can see that there is a salt at 0, 0, and 0, 1, and 0, -1 are the other locations. All right. With that, let's get on to some more serious coding. I'm going to show how you can create some methods to make your job a little bit easier when it comes to coding. Let's start with some housekeeping first. I'm going to add these 2 dictionaries in from my code. The first one's the elemental dictionary. This takes the numbers that the computer will often spit at us and turns it into a string that's more human readable, so we can see what the computer is doing. The second one is the command dictionary. This lets us type in a string, and the computer will understand that we were talking about the specific bit index. It's funny that this bit index later gets traded back into a value, but you know what? I'm okay with that. Now, this is Python. I'm not here for my ultra efficiency. With these 2, we can hopefully have our code be a little bit easier to understand. Next thing we're going to do is add those aforementioned methods to add basically items, arms, tracks, the lot. The first one I'm going to do is do add regular. This is just the average item. It's going to take a name, a position, and a rotation. All right. Now, obviously, this is going to start by adding something to the part list. So we're going to add part array dot append something. What's it going to append? Now, it's going to be an om.part, obviously. What's the name going to be? Now, this is the most useful part, in my opinion, is not needing to type in om.part.something. Now, how can we do that if we're only going to take in a string? Now, Python, we're fortunate, has something called the getAttribute function. This basically lets us dynamically change and access different attributes. So we can do om.part, comma, then a name, and that means that when a name, like a string, comes in, for example, it will automatically basically stitch this with whatever we've done. Let's say it's, we're going to call it add regular, and let's say bonder. And with that, this will add in om.part.bonder. All right. Next, we're going to, hold on a second. Next attribute is going to be position equals pause. And I mean, I don't really think it's controversial. So the third one is going to be rotation equals rot. With that, we can now add a bonder at, 0, 0 with a 0 rotation and just see what happens. Going back into our spadebot solution and pressing F10, there it is, there's our bonder. If we were to instead make rotation 1, it automatically updates it. And in my opinion, this is much more readable when you have 50, 60, 100 of them stacked on top of each other. So we're going to be adding a lot of things. However, this does not work for arms. So let's make a new method called define arms. It's going to be here that you might think of a different way that you want to program this yourself. Again, this is an intro tutorial. I'm doing a few things less efficiently than I could be to make it more clear. If this is not how you want to do it, you want to have one method and you can think of a very clever way to do it, feel free to be my guest. You can do whatever you want as long as it works for you. Now, obviously, arms are going to have a name, a position, or rotation, but we also know they have a length. We also know that they have instructions. Now, I'm going to keep it as length for now. We're going to come back to the arm list in a little bit. Just trust me, though, that it does make sense. There is going to be a list of arms later. For now, we'll just do length equals len. Now, if you're wondering how to code this, that is, that is a point that we will get to soon. Add regular bonder. Instead of that, we're going to add arm. Apologies. From with arm1. And the length is going to be 3. And there we are. There is a 3-length arm right here. The last thing I'm going to add is add track. Add track is just going to take the list of positions and append a part. Obviously, we know that the name is always going to be track, so we don't even need to do this get attribute thing. We can just om.part.track. Then we don't need any of these things because we remember, of course, using our big brain, the track hexes equals position list. And there we go. These 3 methods will hopefully make the rest of our coding a little bit easier. It's at this point that you might be wondering to yourself, what are we actually building? Like, what is the point of this tutorial? I'm going to show you right now what our final goal is going to be. I'm going to pick a better shaped reagent for it first, though. So let's, of course, just staple these guys on. Let's put a gold and a silver. There we are. What would be a nice thing for our bot to create? I'm going to show this off first. Now, I thought that I was a genius when I first discovered this. I thought that I was the first person to think of it, only to see that literally every other bot was doing the exact same thing from way before. So I'm not going to give any credit to any specific person. I don't know who created this. I was so sure that I was, brilliant. I was certainly not. But the idea is as follows. If you take a reagent like this, let's imagine the bottom row. There are only 3 ways each element can be connected, either up and to the right, up and to the left, or horizontally. Meaning that if you were to pass it over a bonder of all 3 types, put down this just so we can run it, you'll see very quickly these atoms at the bottom all get completely dismembered. All of these are completely free elements. They're floating. They do not have anything holding on to them. Meaning that theoretically, if we wanted to, now let's say that we do want to, of course. At this point right here, obviously that's the final one. Cut that out. I just want to show this off in like the easiest to understand way. I'm going to say it's like this. At this point, 4, 5, and 6 are going to trigger. Is going to rotate and drop its element right here. And then ideally, all of these are going to move together. Then the next one is going to drop their element on that square. And they're all going to move. And then the next thing is going to drop their element. It's going to crash. But let's imagine we have a disposal right here. This is actually a pretty elegant way of disposing of an entire element. You can see that the entire bottom row would now be gone. There we go. Now all we need to do is move everything back 3. Obviously, go. Actually, sorry, I apologize, 4. And then we can do the exact same thing again. Let's have them all move down 1 row. And I do know this is hard to follow right now. I hope that when you see the final thing, it will make more sense, but this is what I want our tutorial to produce. As you can see, we're back here again. Before we do the -3, let's do this exact same thing again. Let's have all of them drop what they're holding. And you can see that the next row is also dismembered. There we go. So now, one last time. Let's do this again. And there we are. Now, all we need to do is go back exactly 1, 2, 3, 4, 5, 6, 7. And all we need to do is open our hand. My goal is to create code that will produce this sequence no matter what reagent. If the reagent's longer, it will automatically add more arms onto the side. If it's taller, it will automatically shuffle through all of this more times. However, with only the height and the width, you can theoretically create a bot to do this very easily. There we are. If we watch this really quick, we can see that our system works pretty well, actually. You know, every single one of these bottom ones gets changed, and then it gets scalped all the way through. And there we go, and it repeats itself over and over indefinitely. My hope is that by the end of this tutorial, we can build this system without having any human input. The first thing we need to do this is the width and the height of the reagent. Now obviously, the game doesn't really give it to us, that'd be a little bit too easy. But we can use an earlier method that we talked about to kind of figure it out. We already know that we can loop through the reagents and the atoms in the reagents. And that we can print the atom positions. Now the interesting thing is that this is all of the x and y coordinates that the reagent takes up. With that information, we can, if we want to, split it into x and y. There we go. And then let's make a list of all the x variables and all the y values. Then we're going to very simply just x values dot append all the x's and y value dot append all the y's. There we go. So if we run that, oops, and then print, let's just do the print the x's. We can see right here, this is all of the x spaces that our thing takes up. Now, of course, width is the biggest minus the smallest. So we can do width equals the max of our x values minus the min of our x values. And we can do a very similar thing for height. Obviously, y value is not x. And there we go. Now, while that might seem correct, because width and height do normally work as max and min, we actually need to add a 1 to these values right here. If it occupies one cell, that would be considered 0 width usually, because it occupies 1 and 1. But we want to include the +1 because everything always takes up space. So, with our width and height now calculated, we can do math based off of them. So, let's start doing that. The first thing we want to do is place tracks. Now, back in our game, we need to figure out how much track we need to place. Now, the first thing, we obviously have our element. The element's going to need to travel one whole width value of itself. Like that. Before we can start bonding. Once it's here, it can hit the first bond. Then it's going to go another width length, and then one more, where it can hit the very last bond. You can see the gold start of the Earth. With that information, we now know that our track length needs to go from 0 to 3 times the width plus 1. Now, if that didn't make much sense, don't worry. When you see it in action, it might make a little bit more sense. But just trust me that I did the math on this. It is correct. This is going to take the form of 0, 1, comma, and then the next tuple, which is going to be 1, 1, and then 2, 1, so on. Now Python has a cool way to do this called list concatenation, where you can say, I want it to be I, 1, where I is in the range, let's say 10 first, and just print it and see what we've got. And you'll see 0, 1, 1, 1, 2, 1, 3, 1, all the way on. So we know that it works. Let's just go ahead and instead of that, we're going to do 3 times width plus 1. Learn to spell. And there we are. All we need to do to add 2 tracks together is addition. So we already know that we're at 3 width plus 1. So let's do 3 width minus I, where I is, of course, going to go from 0 to the width. I will acknowledge I'm going through this a little bit fast. Hopefully, when you look at this, it does make sense what I'm trying to do. Oh my god, it overlapped. Sorry. Minus 1. And there we are. Beautiful. This is the track that we need for our system we're trying to create. Next thing we're going to do is add some arms onto it. We want 3 arms, because the width is 3. And we want 3 arms here, for the exact same reason. Let's go ahead and do that. So let's say for I in range width, let's add an arm. I'm going to make this one a piston, of course. And the first row is going to go 0, 1, 1, 1, and 2, 1. So we're going to do I, 1, and then the rotation is going to be 1 and length is going to be 3. We can then copy this code and do the exact same thing at the level 0 instead of 1. Let's go ahead and run that. And there we are. There are arms. And the cool thing is that this is going to dynamically adjust. So let's say that I staple some quintessentials on there. If we run our code and press F10, there it is. It's now 5 times longer and can adjust the whole reagent. Now, one thing that's interesting when trying to place this reagent that you might notice is that when you only know the width and the height, you actually don't know where to place it. This is because while this is a 5x3, this is also a 5x3. We don't know where on we're actually placing. To do this correctly, I like to make an X offset and a Y offset. And this is incredibly easy to do given that we already have a list of every single X value and Y value. So I'm going to go in really quick and type X offset. It's going to be the opposite of the minimum value, right? The minimum is as far to the left as you can, so you add on that value, and then it will always put 0, 0 right here in the bottom left corner. So it's the opposite of the min of the X values, and the Y offset is the opposite of the min of the Y values. Now, how can we use this? We are trying to place our reagent, but where do we want to place it? Let's pop back into the game and say if we have this, we want 0, 0 to be right here. So it's going to be 0, 1, 2, 0, 3 plus the X offset plus the Y offset. So let's write that down. Let's create it's going to be add regular with input is the name. And it's going to be position 0, 3, but 0 is going to have the X offset added, and 3 is going to have the Y offset added. No rotation. If we run that, there it is. It pops right in. But the interesting thing is that if we make this crazy large, it will again dynamically adjust. Right now, obviously, it's overlapping. That's terrible. If we run it and press F10, there we go. Our arms get wide enough. We now have a system that takes the reagent input and automatically form fits to it so we can start our process. Our next job is to figure out where the bonders, or I guess the debonders, are going to go. Looking back at the game, I am going to make a much smaller reagent so we can more easily like conceptualize what's happening here. There we go. We know that we want our debonding array to be in this vicinity, and we know that it needs to start at the end of the second width, right? So here is 0. This is the first width. This is the next one. This is the next width. We want to put it right there, at basically 2 widths. But we're going to do -1, of course, remembering that 0 is technically 0 indexed, as this is the 0x. We go 1, 2, 3, 4, 5, 6, -1, that's going to be 5. Let's go ahead and code that real quick. We know that the first bonder is going to be add regular, unbonder, and we know it's going to be at 2 times width plus -1, comma, what's the height? 0, 1, 2, 3 height. And the rotation is going to be 1. If we run that and press F10, there we go, in the perfect place. So we can do the same thing using intuition. This one's going to be rotated 0 because it's flat. And there's going to be no width. And I know that the third one is going to be +2, not +1, for the offset. And rotated twice. If I press F10 again, there we are. There's our full array built out as we would expect in the exact right place. With that, we've actually put down all of the physical pieces that we need to write our code. So now what we need to do is basically code the machine. We have one issue with that, of course, which is that we don't actually have the references to the arms anymore. When we create all of these items, we have the name, the position, the rotation, the length, but arms specifically also have a thing called instructions. Unfortunately, due to the way that we've built this up, we actually don't have access to these arms anymore. We can't interact with them. We've lost the reference. So the way that we're going to do that is actually by writing an arm list. We're going to take our arm equals this value. Now I'm a perfectionist, so I'm going to quickly get that looking pretty. There we go. So we have an arm. We're then going to append that arm to the part array, but also to whatever arm list we feed in. This is really handy because it means that when we're creating the arms, we can put in an index, and then we can use it later to access them afterwards. Let's see how we could do that. Let's call this one top list, or top arm list, empty. When making the pistons, we can then add in top arm list. We can do the same thing on this bottom one, obviously calling it bottom arm list. And add that on right here. And when we run it, everything on the other side seems exactly the same. Obviously, when we press F10, all of our arms are in the same place. But the key difference now is that when we run, let's say, print top arm list, and you'll see there are 3 OM parts in the list. What this means is we can say for arm in top arm list, arm.instructions equals something. And that will let us dynamically basically change the instructions as we go. This is a very key piece to making this whole thing work. However, having the multiple different arms all work together is another problem. I'm now going to show you how to make some methods to help add instructions in a way that won't cause problems. And the very first thing I'm going to do is at the top, which is not always great practice, but I feel like doing it, so I'm going to do it. I'm going to write global count, basically making a variable that can be accessed anywhere, and setting it equal to 0. I'm then going to make the same global count here. This basically means that we can have a cycle count that is indexed by many different methods in many different parts of the code that are always updating correctly. So when something gets added to one arm, the entire buffer gets changed for everybody. And that is an extremely valuable thing for us to do. All right, with that done, let's go ahead and make some new definitions. This time for adding instructions. It's going to be called add instruction. And I'm going to make it take an arm list an instruction, and a number of times to repeat that instruction. Let's say that we want to have it grab something 7 times. You would add in the number and the instruction. Let's go ahead and do that. First of all, let's do global count, of course. Then for I in range number, and we're not going to use that I at all. We're just going to have it repeat the number times. First thing we're going to do is going to do for each arm in the arm list. And that's just so that we can change that arm specifically and then get through all of them before one full rotation is done. We're going to do arm.instructions.append. And this is kind of the one really long thing. It's going to be an om.instruction. Now, an om.instruction needs 2 things. It needs the count, which is the value where to put it, and what type of instruction to do. Now, if you remember up here, we basically made a translation codex to go from strings to the bit code. So I am then going to do that instruction from above, the command dictionary, taking the instruction we were given as the index. So if we type in armlist grab 5, it's going to run through 5 times, and each of those 5 times is going to put the grab on each of the arms. And then, of course, grab is going to look through here and put the bit code in. The last thing we need to do is just update the count. All right, and that's actually all we need to do for this method. That's done. We can test it out by going to the bottom, of course, and let's try it out. We're going to add instruction. I'm going to do the top arm list. I'm going to make it do the, what's it called, the track plus command. I'm going to make it do it 8 times. So if we run that and test it out and press F10, there it is. 1, 2, 3, 4, 5, 6, 7, 8 pluses appear on the top. Obviously, we put this down. It works. It actually works. And that is extremely cool. But while that is nice, there is a second instruction method I want to add, just for like kind of ease of use. Technically, we could do it with what we have currently, but I like having this one as well. So I'm going to copy this in and make a second version. But instead of add instruction, it's going to be add instruction list. And instead of taking in one instruction, it will take in, shockingly, an instruction list. But no num. Then, instead of doing for I in range, we're going to do for instruction in the instruction list. And there we are. That's actually all we need to do to basically make the instruction list. Let's test that one out as well. This time let's do the bottom arm list because I feel like it. And to test it out, we're going to have an array. And let's have it grab plus and drop. Running that code and pressing F10. There it is. Grab plus drop. All there in one really nice and easy to see spot. With that, we can actually start building out our solution. Let's think about what needs to happen on the actual instructions belt to make everything work. To start, everything needs to grab and plus 3 times. Just logically, we know that's true. It's the width, of course, not 3, but still. So let's look at what happens. And here, at this point, we're going to build a for loop. Everything that happens from this point on is going to happen over and over and over until there's nothing left. We'll have it go an additional 4 to the right. For me. And then it's going to do that weird spillover thing. Look at that first step done before we go any further. Now we have the top arm list and the bottom arm list, of course, but I think we should make a full arm list, which is just, of course, going to be the top arm list plus the bottom arm list. Nothing too revolutionary here. All right. So here's going to be where the actual coding for the machine is. We're going to do full arm list. And we're going to start it off with grab once. There we go. Then we're going to have track plus 3 times. Obviously, if we pop back over, this does exactly what we'd expect. 1, 2, 3. Next, we're going to do, let's say, to do make for loop. Beautiful. We're going to have it, 3 should be width. And this value is going to be width plus 1. One thing that just occurred to me looking at this is that we actually don't have the disposal glyph down. Obviously, an arm is going to be placed right here. So our glyph is going to be put right here in the center. Let's count that out. That's 1 width, that's 2 widths, that's 3 widths, plus 1, 2, 3. All right, so I need to put a glyph of disposal at 3 widths plus 3. Go ahead and do that really quick. Add regular disposal, 3 times width plus 3, comma 0, with no rotation, of course. Running that and pressing F10, perfect, it's in the exact same spot, but let's go ahead and stress test this as we always should by adding on something that changes values drastically and just making sure that it puts it in the right place. Beautiful, that's what you want to see. That arm right there is still going to reach to the exact same place. Cool, that was an important piece. To be honest, I'm a little bit upset with how ugly this code looks. I know this is a tutorial, but this is bothering me a little bit. I'm going to be right back. I'm going to quickly edit over our code a little bit, just make it a little bit more readable, hopefully a little bit more enjoyable to look at. Alright guys, I did a little off-camera mining, and we have a little bit of some cleaner code. For the most part, everything is exactly the same. I've just basically tagged it, and I've ordered it in a better way. I moved the full arm list next to the other 2 arm lists. I put all the builds together and all the coding together. The one thing that is new though is this right here. I added an output, and I just put it off to the right. The only reason I did that is because I don't like getting this all products must be placed message, which stops me from just running it automatically. Outside of that, everything's exactly the same. So let's move on to the next step. We need to figure out how to access each arm individually to make each arm independently drop its reagent in order. The good news is this is actually a pretty easy thing to do because of the way we set this up. We can do for arm in bottom arm list. And there we go. That's going to be 1 arm at a time. Unfortunately, it's going to access this arm, then this one in that order. Obviously, we want to do right to left because we are moving to the right side of the screen. So all we need to do, this is a very handy trick. If you do that : -1, that actually reverses the list. So this is now going to grab the arms in the opposite order. That's all we need. Next, we're going to add instruction list. And we're going to put the arm into a list just so that it can actually run and not crash. This is an annoying quirk of the way we set things up. And we want both of those arms to do 2 things. We want them to rotate clockwise, and we want it to drop. If we run that as is, we can see that it basically works. It's going to drop right here, and the next one's going to drop. The only issue is that they're not all moving together. Let's add that in. Let's add an instruction. Let's just do a regular instruction for all arms. So it's going to be the, actually all the bottom arms. It's bottom arm list. We want all of them to do the track plus. We want them to all do it 1 time. Let's see if that actually works. Amazingly, it 100% does. Now, it's not as impressive on this one with a bunch of blank space. Let's go ahead and build a little bit of a denser object. Let's see what happens if we run it on this instead. Obviously, it's going to be floating right now. But if we run our code and press F10, look at that. I mean, that's just really cool. Our code is doing exactly what we want it to. All right, let's go ahead now and add the next few things. From here, things are going to start moving a little bit quickly. I mean, the bot kind of just starts writing itself. To start, we're going to add instructions, do a bunch of minuses to the bottom to put them right back in their right place. That's going to be a width amount of times. And then, of course, they're all going to have to pivot back. I'm going to do add instruction to the bottom again. That's going to be rotate CCW this time instead. And then, of course, it's going to happen once. From there, and now all of the arms are going to start moving. They're going to all move left, and it's going to basically counteract this right here. We can copy this right here, but instead of track plus, we're going to write track minus. And from there, we've actually made a lot of progress. If you want to run it really quick just to look, press F10. We're back here. We are basically in a position where we can redo our for loop. Really, all that's missing is us pulling down what's left of the reagent so that we can grab it on the next go around. Let's add that right now. Let's add an instruction list. This is going to be for both arms, of course. First thing it's going to do is retract. Then it's going to drop. Then it's going to extend. Then it's going to grab again. And the crazy thing is that once we've grabbed, we can actually just pull back right here. We're back and we can plus and do the whole disposal thing. And then we minus. And then we retract, drop, extend, grab. So with that written, we can actually just write a for loop. And it's going to be for I in range height. It's just going to loop a height amount of times. Let's run that really quick. Press F10. And watch this. We are almost done. The only thing we're missing is undoing the very beginning part, actually, where we do the plus and then let go. Let's go ahead and add that, of course. That's going to be after the for loop is fully finished. We're going to minus a few times. And we are going to drop, just so that the arms are open so they can grab again. Let's run it. We can run it again. And it's consistent. I'm very proud of this. I think it's very cool. I think this can actually be used in the competition if you really want to. You know, you'll have to do a little bit more on the other end to put it back together. But this is a very real thing. This is a very real system that's useful. So let's go ahead and stress test it, because that's what we all love doing. All right. Pop back in, run our code, and see what happens. Frame rate's struggling a little bit, of course. And although my game was struggling a little bit, it fully works. It decomposed the entire thing. The final question is, what do we do with this? Like, what was the point of building this? I'm going to show you one pretty good example to hopefully explain what benefit we actually got out of making this machine. I'm just going to go ahead and create a reagent that has a fire and a lot of salt. I'm going to change our output to just be one fire. Okay? Now, popping into our codex, let's quickly run our code, press F10, and this is what we're left with. Let's imagine instead the output was put right here. All I'm going to do is remove this left and this right. Let's watch what happens. We have actually solved this puzzle now. Now, interestingly, if we wanted to, we could put an arm right here and have it get processed, have a second chamber that reconstructs. Grab a fire, a salt, a fire, and a salt after decomposing 3 full elements. and you can have that be reconstructed right here into any shape you want. And that's the full power of this system. By making something modular like this, you can then, in your code, write a second half of the function that then recomposes the element on the other side. Now, obviously, there's a lot more that could be said about this. Most Opus Magnum puzzles actually have you change the elements before they get to the output. Stuff like metals or Berlow's wheel. Things like that you will need your code to consider before pulling the specific inputs in the specific order they're pulled. But that being said, this system with only two if statements, which will pull out this right here and this right here, can actually solve a level. And I think that's extremely cool. With that said, there's one last interesting thing I want to talk about. In my experiments, this system can break down almost every element, but I actually found an edge case that it breaks on. If you think about it right now, what type of reagent do you think would break this system? All right, now that you had a moment to think, is this what you had in mind? This shape right here actually bricks our entire system. Let's go ahead and see, by pressing F10, what actually goes wrong. And there we are. It's pretty simple, actually. As our element moves to the right, it gives the original element enough time to spawn in and causes a collision. Now, I know that theoretically I could show you a way to solve this problem. That's not the reason I'm showing you this. No matter how many edge cases you prepare for, you're always going to get screwed over by something. There's always one weird edge case you didn't consider that is the perfect thing that breaks your bot, and it breaks, right? It's going to happen. I can guarantee you, no matter how much thought you put into this, you're going to miss something. So this is a reminder to build some more robust code. Instead, have it go through. If it breaks for some reason, just have it tell you. Have the system print out a statement saying, puzzle 385, I wasn't able to solve it. I used OM.sim, I tested my solution, it did not work. You go in and figure out what's wrong. Because to be honest, the time spent programming every edge case, in the grand scheme of things, it's just faster to go in on the day of and do it yourself. And with that, we've reached the end of this video. I know at the beginning I mentioned some higher level concepts, but to be honest, I sprinkled that stuff in throughout the video as best I could. In all honesty, what we've made here today isn't actually that far off what I have in my personal project. I mean, mine supports 4 inputs, mine has more computation, but to be honest, you have unlocked a lot of the programming knowledge that I have when it comes to Opus Magnum. I really hope this tutorial helped someone. If that person's you, please leave a comment. That stuff makes me happy. I like to know that what I'm doing makes a difference to somebody. Thanks for watching. Happy puzzling, and good luck out there. I hope that this video lets you make something cool that you're very proud of.